Okay, so hi everyone. Thank you so much for joining this session. We are into module 6, as Saina just mentioned. We are going to talk about more advanced Wi-Fi use cases. So this is a little bit more onto the business end of Wi-Fi. So far in the last module, we have been mostly talking about the very technical aspects of the standard extensions. In this module, we are covering more on the little bit more on the business side. So it's not hardcore technical content for the next 4 sessions, but it is still very relevant to our day-to-day lives when as a Wi-Fi engineer. As to quickly summarize the last module that we did, as Sainad mentioned, we went into the advanced MAC features, talked about 11K, VR, fast roaming, RRM, DFS, and other things. We talked about the last 3 big standard extensions for Wi-Fi in the 3 sessions. Wi-Fi 6, we talked about OFDMA, multi-user MIMO, BSS coloring, target wait time, and all of that. And then we talked about the 6 gigahertz spectrum, how the 6 gigahertz spectrum got opened up, and that opened up a lot of new opportunities for Wi-Fi. 100 megahertz of new spectrum available in the 6 gigahertz band. And we talked about how that enabled for larger channel bandwidths and also more restrictions for device classes. We talked about standard power and different types of power categories that we have for devices that are used. We talked about AFC, and because of the bigger spectrum becoming available, that fundamentally changes how we scan for channels, because there are a lot more non-overlapping channels available in the 6 gigahertz bands. We talked about new methods in which we do scanning, and we talked about fills, preferred channel scanning, reduced neighbor reports, multi-BSSID, and all these other features that are part of Wi-Fi 6 E 6 gigahertz extensions. And then the last session in that last module was about Wi-Fi 7. That really brings us to the latest and greatest in Wi-Fi. We talked about all the new features, or at least most of the new features in Wi-Fi 7, including 4K QAM, 320 megahertz. We talked about the very important multi-link operation, or MLO, multi-RU of DMA. We talked about multi-AP coordination, preamble puncturing, and number of other features. So if anyone missed any of these sessions in these modules, they should be available on our website. All the videos, the class notes, and also the slides are all uploaded there, so you can go watch it there. So as I said, module 6 is the current module. We will have 4 sessions here. Today is the first session. So we are going to talk about advanced Wi-Fi use cases. Today's session will dig deep into understanding both residential and and enterprise Wi-Fi deployment models and various use cases, and how the routers, access points, and controller architectures, the concept of thick APs, thin APs, physical controllers, cloud controllers, CAP-WAP protocols, and so on. So we're going to talk about all of those exciting things today. And then the next 3 sessions are going to cover other more advanced use cases like smart Wi-Fi features, mesh networks that are very popular both in the enterprise and in the residential deployments. We're going to go into detail about that. And also in the last session, we're going to talk about Wi-Fi monetization, how Wi-Fi technology has really helped improve operations of enterprises, and how IT really helped with operational technology, and some really cool things to talk about in that session, of how Wi-Fi can really not just provide network access, but in many ways optimize business operations and really provide very good ROI for the companies that are deploying Wi-Fi networks. So we're going to talk about that in that session. Okay, so jumping into today's session, of course, if you are joining us for the first time, you can access the course webpage. All the content is on, all the courses in the webpage. And then if you're registering here, there's a registration link where you can get the regular meeting invites for all the sessions. And then you could also join the WhatsApp group if you want to get updates. Okay, so moving into today's session, first part of this today's session is going to cover the residential space, and then we're going to move into enterprise. And in the residential use cases, we kind of touched on this in the part 1 of this course. The very early Wi-Fi routers were low speed and looked very, very simple and costed a lot less money. And then they were mostly doing DSL backhauls or phone line backhauls, POTS backhauls, and things like that. and they had very low security, no QoS, and really meant for providing wireless access for one or two wireless devices in the home, basically running email and text applications. And after that, the Wi-Fi router started becoming a little bit more complex. We started to see multi-band access point deployments. So we started seeing routers like this that have multiple antennas, MIMO technology, multiple bands, multiple radios, and then the backhaul is over fiber. We started seeing gigabit Wi-Fi fiber deployments, or fiber to the curb or fiber to the house, and coax connections that are providing internet connectivity in the home. And then the operators really started picking up Wi-Fi, right? And they started deploying these Wi-Fi and started managing the Wi-Fi routers in the homes. And we started seeing managed Wi-Fi networks where the operators would provide not just the internet connectivity and not just the cable TV and phone lines and content, but they would also provide the Wi-Fi routers in the houses. And then we started seeing voice, video, and more delay sensitive applications. And after that, the router started becoming even more bigger. As the applications started becoming bigger and bigger and more important, the routers also started becoming more and more bulkier and more expensive. So we have these like really heavy routers, right? So these are much bigger routers that you have, a lot more antennas, a lot more radios, and a lot more expensive. Like some of these routers could cost like $500, $600, maybe over $1,000, right? And we started seeing this big bulky Wi-Fi routers. And then this was also the time when mesh became very important, because the houses started getting bigger. People started having 2, 3, 4 TVs in a house in various locations, all streaming content over Wi-Fi, which means that you need to get really high bandwidth all the way to the edge of the cell, which means that you need to deploy mesh technology. So mesh technology became real popular in home. We started to see 1 node, 2 node, 3 node mesh networks, repeaters, and so on. And then we started seeing technologies like community Wi-Fi as the operators started managing the Wi-Fi networks, and they started to bring like 1 gigabit per second fiber links to the house. They started realizing that there is so much bandwidth available that can be shared by the community. And so there are technologies like community Wi-Fi that came out. And of course, as you deploy Wi-Fi routers and more people are using Wi-Fi in the house, including our kids, it is very important to have good parental controls. So there are lots of really new techniques when it comes to parental controls and other things, where you are almost using the Wi-Fi router as an application level stateful firewall that can actually basically block traffic, shape traffic, and so on. And of course, the applications also started evolving. We went from voice and video to OTT, over-the-top content, more video streaming, gaming, and so on. And if you look at the current generation of Wi-Fi routers, which is where we are right now, again, the Wi-Fi routers got even bigger. So you can all see this is an example of a big router. It's bigger than my head. And this is the latest Wi-Fi 7 router that we have from TP-Link. And you can see that this is really big, and it has a lot more antennas and more radios. It supports a 6 gigahertz band, and the router started becoming bigger and bigger. And we started really going after much higher bandwidths, well over 1 gigabit per second throughput. We started to see different types of backhaul links like satellite backhaul and so on. We started to see the Wi-Fi router not just providing internet access to your laptop and your smartphone, but also managing your home automation devices. And you're creating a connected home, and you're seeing high density deployments in a house. It's very normal in a home to have like 10, 20, 30 Wi-Fi devices of different shapes and sizes that are all managed by the Wi-Fi router or some form of home gateway. And we also started seeing the applications like AR, VR, gaming applications come across that are super low latency requirements, high density, very low latency requirements, high throughput, and home automation. All these things started happening really well as we started the evolution of Wi-Fi. And all of this happened over the last 15 years or so. And there is so much more advancement in technology, as we can see. So we'll talk about some of these use cases in the residential side, and then we'll jump into enterprise. And residential, the operators, or what we call as the service providers or the cable companies, started managing Wi-Fi networks in the house. Let's say we want to get internet connectivity from, let's say you're in India and you want to get it from Airtel or Reliance, one of your operators, or in Europe, maybe from British Telecom or Sky or someone like that. Normally, they provide you the internet connection, which means they bring the fiber connection, the ONT and the modem to your house, and then they also supply a Wi-Fi router with it. Right? So you can either go use the operator's provided Wi-Fi router, in which case they will configure the router for you. They'll set up the network. They'll make sure the network is working. They'll make sure the devices in the house are able to connect to the Wi-Fi network and get access to the network. And then they will manage their entire network, the access network, the router, the switch, the access point. All those functionalities are managed by the internet service provider or the operator. That is one model. The other model is where the operator will bring the ONT or the fiber connection and the modem to your house, and then you would connect your own Wi-Fi router to it. Many of us have our own Wi-Fi routers because we may not like the routers that are provided by the operator. So we can set up our own Wi-Fi router, and in which case we will have to configure it ourselves. We have to basically set up the SSIDs and the network security, and also manage it from its web app. So we need to connect to its web interface and then program the router the way we want it. So there are both overall there are managed networks and unmanaged networks, and they're done by the operators. Now there are some advanced features that I was talking about, like parental controls, which is pretty cool. For many years, people were buying Wi-Fi routers for more speed. So Wi-Fi router gives me like 1 gigabit per second, 10 gigabits per second, 20 gigabits per second. So speed was one of the main reasons. The number of radios, the range, all these things were a number of reasons. But as the Wi-Fi router started getting evolved, it is more about the software now than the hardware. So what can the software do for you? What kind of features and functions can it provide? And one of the really cool features is parental controls, where in many ways you are running almost like a full firewall of inside the Wi-Fi router, which means that the Wi-Fi router is not just a layer 2 device anymore. It's not just basically converting Ethernet to Wi-Fi and Wi-Fi to Ethernet. It is actually doing deep packet inspection. It is going through all the layers of the OSI model and basically decoding, going through all the headers and identifying application layer traffic and applying certain policies based on that. And this allows us to apply different types of controls on a Wi-Fi network. So now you can have smartphone apps where you can actually connect to your Wi-Fi network and control various things on the Wi-Fi network. Like you can track the number of devices that are in the home. You can customize the internet bandwidth and rate limit certain bandwidth for various members of the family and guests. So let's say there is a guest in your house, you can set like, I don't know, 10 megabits per second rate limit for a particular user. You can set like maybe 1 Mbps rate limits. You can do rate limits per user. You can set screen time limits. Let's say for your kids, you want to limit the amount of screen time for them. So you can say, okay, person A or my daughter, who is like 7 years old, gets only like 1 hour screen time in a day. And after that, our device stops connecting to the Wi-Fi network because that's the limit that I've set on the Wi-Fi network. We can also track usage of history of websites. Again, this is part of the deep packet inspection, where the router is getting deep into the packets and trying to identify the applications and the traffic patterns. You can filter content based on age group, based on type of font. For example, I can say for my kid, they're not going to allow certain OTT platforms or certain applications or certain types of videos, right? We can do interesting things like pause Wi-Fi. For example, as a family, we're all sitting together and having dinner, and let's say at 7 p.m. we want to say pause Wi-Fi, and we put a pause Wi-Fi button, and then it's going to just disconnect Wi-Fi for everyone. You can track locations, you can set bedtimes, rewards, all kinds of things can be done as a part of the parental controls that most modern Wi-Fi routers will have. And of course, most modern Wi-Fi residential routers are not just providing internet access to everyone. They are also in many ways managing the entire smart home. And the smart home can be, of course, managed by the operator also, right? So there are many components in the smart home. There is the home media gateway, or the basically the hub. We have like devices like Amazon Alexa and Google devices, Samsung smart things, other devices that act as the hubs that can talk to all these sensors and IoT devices in the home using possibly other wireless technologies like Bluetooth, Zigbee, Z-Wave, and other methods. And then they will connect via Wi-Fi to the access point. And then we also have the various smartphone apps that will actually control these devices, a smartphone, and then there is connectivity with the cloud, like an Amazon cloud or the Samsung cloud, where all these devices are provisioned and managed from. So this is the entire smart home architecture where you have many different devices of smart homes, like smart locks, smart bulbs, smart switches, smart thermostats, and smart cameras, and smart sensors, and all these devices could be part of the home network that are being connecting to the cloud through the Wi-Fi router and managed through various applications. And Wi-Fi routers now play a big role in making this happen. And of course, one of the trends that we have noticed, and this came about 4 or 5 years ago. I'm not really sure how much is it used right now, but at one point it was kind of heavily publicized, the idea of a community Wi-Fi. Remember that most modern homes get up to a gigabit per second, in fact even larger fiber links to the house. That is a lot of bandwidth. 1 Gbps is a lot of bandwidth, and it's not very normal to that you will need all the 1 Gbps in your house. So you can open up some of that bandwidth for public use as a part of the community network. So if your router is part of the community network given by the operator, then the operator will automatically put a community SSID, a public SSID on this device, which is basically segmented and open for public use, and that is part of the public infrastructure, public network. So all the security credentials and everything is part of the public network. And as far as the Wi-Fi router goes, it's a separate, basically separate virtual network, and it's completely segmented. So although you're using the same physical router, virtually they are different networks, right? And you are using the bandwidth that is coming to the home, but then you also need to make sure that the private SSIDs and users in the home are getting enough bandwidth, right? And that's normally how community Wi-Fi works, where especially if you are living in an area which is heavily populated in metropolitan like cities and large apartments, if you want to open up some of the bandwidth for public use, the operators can do that. So these are some of the use cases and trends that we have seen, at least in the residential Wi-Fi space. Now, of course, the operators manage the residential networks for you. What we see in our homes is only at the very end in the home, right? We see this app section and the home section, but then there is the last mile section, there is the backbone, there is the internet, and then there is of course the cloud and the provider networks. And these are all the things that are in the back that make all the things work for us. If you go to our house, we watch Netflix, we watch YouTube, we connect to a network, we use our smart device in the home. All of that we do, but there is an entire network behind that that actually makes all of these things possible. And it is pretty complex and pretty impressive. So at the edge, we have, of course, the access points or the Wi-Fi router, which is normally connected to an ONT or what we refer to as a customer premise equipment or a CPE device. Many times you will see the CPE and the Wi-Fi router integrated into one unit. So that is just a single unit. Sometimes you will see multiple. So you see a separate Wi-Fi router and you see a separate CPE device. And that is normally connected to over fiber link to a more aggregator like a DSLAM
switch, and from there, from the link aggregators, you actually go connect to the IP network. So then from the optical network, you go on to the standard internet, the typical IP network, and then you also have various other elements like the content caches, where the content is cached for OTT, and also you have basically the gateways, the internet gateways, and from there you go on to the edge point of presence, the edge POPs or the edge servers that are providing basically point of presence to the local area. And then from there you go to the backbone of the internet, and then from there you go on to the data centers where you have all the content that's being streamed from. Right, so there is an entire complex operator network for residential Wi-Fi. Parts of this network are also shared for cellular and also other types of edge network access. But we are just drawing this. This is a diagram that shows just for Wi-Fi edge networks. But this is just the edge. But this is entirely, there is so many things that happen behind the edge of the network. So that's pretty impressive how much work that the operators do to bring the Wi-Fi access to our homes. So that's a quick kind of summary of the architectures and basically the evolution of residential Wi-Fi and some of the new features that we saw. So now let us move on to the enterprise network and try to tell the same story of how enterprise networks evolved and what are some of the ways in which enterprise networks and Wi-Fi networks are deployed and what kind of architectures and we see here. Of course, the story is very similar for enterprise. It started off with a very simple Wi-Fi router or an access point that's in a small office environment, and it's typically providing wireless access to 1 or 2 users and no security and email and text. And then after that, we very quickly started seeing large-scale deployments of Wi-Fi. So immediately in enterprise, the one thing that is fundamentally different from residential to enterprise is the scale aspect. In enterprise, we are looking at large offices, large stadiums, large hotels, and many other large public venues where we expect to have hundreds and hundreds of users spread across a large space, which means that we need lots of access points. And very quickly, the enterprise deployment started realizing that managing all these access points at scale is not going to be easy. And then from there came the concept of a controller. And the idea of the controller was to actually have centralized management of all the wireless access points that makes the management easy at scale. Right? So then the concept of controllers came along. And after that came the concept of distributed enterprises. So normally we went on from a small enterprise that has like a few people to a large enterprise that has a large concentration of people in one location. Let's say you have let's say an office like ours here, and let's say we have 50 people sitting here all in the same physical location, and we have several access points. So from there we went on to what we refer to as a distributed enterprise. So what is a distributed enterprise? Where you have all the workers and locations distributed all across the world. So if you look at a global organization, it could have an office in the US, it could have an office in Europe, an office in India, different sizes of offices. Some of them are big, some of them are small. We have a number of people working from home. So we have home offices. We have a number of people working on the go from airports, from hotel rooms, and so on. So that is also a mini office on the go. So we need to actually manage this distributed enterprise, which could be spread across many locations from a centralized in a centralized way. And with the internet speeds going up, picking up, the concept of cloud controller came along, where you can actually manage your entire distributed network from the cloud, right? And that's where the cloud controllers came along. And then, of course, the latest buzz in the enterprise world is all about, of course, even higher speeds, IoT, and all these things are there. But one of the bigger things is how can you introduce artificial intelligence and machine learning techniques in Wi-Fi, and how can you actually make the installation, deployment, and maintenance of an enterprise Wi-Fi network a lot more easier. So the idea here is, again, to replace or at least make the job easier of a highly of a highly technical IT person. So if the network itself is able to manage everything, is able to troubleshoot itself and heat itself, then we don't really need a human being doing all the analysis and troubleshooting, right? So that is the whole idea behind making the networks more intelligent and more self-aware. And also this concept of network as a service started coming along, where up to this point, mostly enterprises would buy the Wi-Fi devices and networks, and they would install it, and someone, the local IT person, will manage it for them. But now there are many companies that are providing network as a service, where you don't have to pay for the hardware. They'll come and install the hardware, they'll manage everything for you, and then you go for a subscription service, right? So that is how enterprise Wi-Fi has evolved over, again, the last 15 years or so, from a very simple single access point model to a distributed, to basically several access points managed by a controller, to a distributed enterprise model, to a self-aware and basically an artificially intelligent network model, and a network as a service model. Right? This is basically the story of enterprise Wi-Fi over the last 15 years or so. So now let us dig a little bit deeper into some of the ways in which enterprise. Now this, from here we get on a little bit more technical, and we try to get into the details of the enterprise Wi-Fi network architecture, and we'll talk about various ways in which enterprise networks work. So as we said, enterprise Wi-Fi networks typically have several access points, and they also have many switches, and also, of course, routers and other network elements that are part of the large-scale network. So, of course, if you have lots of access points, you need switches to provide power and also provide basically cabling and connectivity to these access points. Now, enterprise Wi-Fi networks have really, the access points can be deployed in three main modes. One is what you refer to as an autonomous access points, or also referred to as thick APs or fat APs. Here, the AP is doing all the functions, and there is no concept of controller here. And then we have the idea of lightweight access points, which are managed by a controller, and then we have cloud-based access points. So these are the three most common types of access points you would see in an enterprise network, and we're going to talk more about those in the next few slides. A typical enterprise deployment, as I mentioned, has multiple access points, and then it has multiple SSIDs. So SSID is, as we all know, is a service identifier, but it's you can also consider this as a virtual network, on a virtual wireless network, basically. So the idea is you might have several physical access points, but you can create a single virtual network, virtual wireless network across all the physical access points, and that is what an SSID is. So you can create SSID 1, and the same SSID might appear on first AP, second AP, and third AP, and it makes it looks like one virtual network. And similarly, you can have several networks, several wireless networks across all the physical access points. So you can have SSID 1, SSID 2, SSID 3, and so on. And so these SSIDs are normally mapped to what we refer to as WLANs, or virtual LANs, on the wired side. And when we are managing these networks, then you use some form of mapping from access points to SSIDs to WLANs. So let's talk about autonomous APs first. So autonomous APs is where the APs are self-contained and they don't rely on any wireless LAN controller. Each AP is individually configured, which means that every AP needs to have its own management interface, its own management IP address. And if you put the AP on the network connected to a switch, the IT person should know the IP address of each autonomous AP, and then they will basically log into the AP either through SSH, Telnet, or HTTP web UI interface, and then they can configure each access point individually. And then if you want to upgrade, downgrade firmware, if you want to change security policies, if you want to apply new policies, all of that has to be done individually on each one of these access points, which is extremely hard if you have a larger network. So autonomous APs are really used for smaller enterprises. In fact, I was surprised to see some of the universities that I visited. they're actually still programming these APs in autonomous mode, even though they have 40, 50 access points, 100 access points. But there are some legacy deployments that still do it in that method. Okay. Now, the disadvantage with autonomous APs is, of course, the configuration part is can be very cumbersome. But the other disadvantage is now you have these VLANs that we are creating, these data VLANs and management VLANs that are spreading across the entire network. So same VLAN 1, which is the same SSID, is across all physical access points. So you need to spread these VLANs across the entire network, and that is normally just considered as a bad practice, which can create large broadcast domains, and basically you'll have spanning tree protocol issues and things like that over a network like that. So now talking about lightweight access points. So lightweight access points are where you actually make the access point simpler. So this is normally how a lightweight access point looks. And the idea, again, there are two fundamental reasons why you have this concept. One is you're deploying lots of access points in an enterprise, so managing all of them individually is going to be very hard. So it is good to have central management. The other main reason is if you push some of the functionality of this router into a central location, then that means that this Wi-Fi access point has to do less and less work. It can actually do what we refer to as the lower MAC functions, and the upper MAC functions can be moved to the controller, which means that this device needs lesser processing power, and which means that you can build these routers for lesser cost. So one of the things you want to do is when you're doing large-scale deployments, of course, you want to save money and you want to save the cost on these units, and you want to make them as inexpensive as possible. And one of the ways in which you can make it inexpensive is by pushing some of its functionality into the controller, right? So scale and cost are a couple of reasons why we came up with this concept of lightweight access points. So lightweight access points use what we call as a split MAC architecture, where there is the lower MAC, which is doing all the lower MAC functions. The AP is done by the AP, like client association, sending out beacons, probes, doing the actual encryption of the data, doing sounding, doing trigger frames, doing block acts, retries. All these things are handled by the access point, which are considered as the lower MAC functions, right? Authentication, association, and things like that. Then they have the upper MAC functions, which is basically the radio resource management, QoS management, load balancing, the traffic shaping. We talked about parental controls. We talked about mobility, authentication, security, at high-level security, and all these other things and policies in the network. They're all managed by the upper MAC, and that functionality is moved from all the access points to the controller. So there is one central controller that is doing all those upper MAC functions for all these physical access points, and each access point is only handling the lower MAC functionality within its immediate wireless LAN cell. So now we have these access points and we have a controller. But the access points and the controllers are splitting the functionality, which means that they should be communicating a lot with each other. So what we did here is we took some part of the access point and moved it to the controller, which means that for the access point to work properly, it has to constantly communicate with the controller. And that communication has to be there all the time. Otherwise, this access point is not going to function very well. And that is the reason why we need a very strong communication protocol between the access point and the controller. And there is this protocol called CAPWAP, which is basically used as a communication protocol between access points and controllers. So the original implementations were proprietary. So most companies like Cisco and Aruba and others who started building wireless LAN controllers had their own proprietary protocols. So Cisco called it LWAP and so on. But then eventually they started creating a standard called CAPWAP, which stands for Control and Provisioning of Wireless Access Points. And then we now have a standard way of how an access point talks to a wireless LAN controller. And normally what we do is we create a CAPWAP tunnel between the controller and the access point, and all the communication between the access point and the controller goes to this tunnel. And then within the tunnel, there are, and again, tunnel is basically a logical entity, right? Of course, the traffic will go through the physical network, through the switches, routers, and so on. But then there is a logical tunnel that is created between the controller and the access point. And normally, for communication between the wireless LAN access point and the controller, we'll have two tunnels. One is basically a control plane tunnel, and one is the data plane tunnel. So the control plane tunnel is used to basically control and manage all the access points. So using the control plane tunnel, there's a specific UDP port number for that, and using that port number and using that tunnel, that link, the controller will control and manage all the Wi-Fi access points. And then there is a data tunnel, which means that all the data that the access point is sending and receiving, let's say the station is sending some data to the access point, that data, rather than going through a switch and a router to the internet, will be routed through this tunnel to the wireless LAN controller, and then from there it goes to the internet. Which means that all the data that the AP is receiving has to be forwarded to the wireless LAN controller, so that the wireless LAN controller can again do deep packet inspection, analyze the traffic, and forward it to the right place, and based on that apply policies and so on. So this is normally how wireless LAN controller basically connect. Will associate with an access point. So there is a process when a client, when we have a client that is connecting to an access point, there is a process for that. Similarly, when an access point is coming onto the network and connecting to a wireless LAN controller, there is a whole process for that. So at a management level, there is an IP address for each access point. The AP is now discovered, so there is a discovery process between the AP and the WLC, and then there is a join request, join response, and then configuration. So and now once the access point joins that wireless LAN controller and comes up within the wireless LAN controller dashboard, the next step is to configure the access point to make sure that you actually check what is the current firmware it has, make sure it has the similar firmware as all other access points on the network, and pushing configurations as again a communication channel on the control plane. And then there is the tunnel maintenance. So as you set up the tunnel between the access point and the controller, you need to maintain the tunnel all the time. So there are some keep alive messages, echo request responses, and so on. And then of course there is the updating the configurations. All of these are message exchanges, CAPWAP protocol exchanges that happen between the wireless LAN controller and the access point. Now of course there is encapsulation as well. So if you take a normal Ethernet packet, that is IP packet that is coming into the local area network. So normally you put a 802.3 or an Ethernet header on top of it, and then it goes into the controller, and the controller adds its own layer on top of it, which is the CAPWAP layer, and that is part of and so it basically adds the CAPWAP header, and then also of course there is a basically control plane UDP and UDP IP header as well, because now it's encapsulated inside a tunnel. So now basically that information is sent to the switch, which is then in turn sent to the access point, and then this is where the tunnel will close between the controller and the access point. Once the data, encapsulated data, gets to the access point, then the access point will take out all the headers that are part of the tunnel, and then you will have the .11 header and the .11 payload, and that is then moved on to the station, right? And then the station again, when it tries to connect to the internet, it has its own payload, which is encapsulated in the .11 header, and then when it reaches the AP will again make it part of the tunnel, so it will add the CAPWAP header and the encapsulation, the CAPWAP encapsulation, and then move it and then send that information to the controller, which will again process it and then send it up to the internet, right? So there's a lot of encapsulation and overhead when it comes to having communication between a controller-based access point. Now, all of this is done so that you can do a centralized management of your access points and also pass all these data from the network to the controller, so that the controller can process that information. Now,
sorry to interrupt. Once, can you have a check at the audio settings? The microphone being used. I think for me the voice is cracking a little.
Okay. Let me see if the voice will come back up. How about now? Voice better?
Yes, I think. Yes, sir.
Can you hear me well?
Yes, sir.
Okay. Sorry for that glitch. So continuing on. So lightweight access points can be deployed in many different modes. The most common mode is what we refer to as the local mode, where the lightweight, and some of these terminologies, different equipment manufacturers have different terminologies for this. I picked up the Cisco terminology, but maybe Aruba or someone else might have a different terminology for this. But since Cisco is the most common, this is the terminology that they normally use. So there is a local mode where an access point will offer a wireless network, which means it's going to advertise a wireless network, a basic service set, and then stations can connect to it, and then all the control plane and the data plane traffic will go through the controller because the access point is basically in a lightweight mode, and all the data plane, control plane traffic will go to the controller and then onto the internet, right? So that's the most common mode in which lightweight access points are deployed. We also have the Flex Connect mode, where the AP can behave as a local AP by default, which is a controller-based AP. But for some reason, if there is a failure on the wireless LAN switch or the controller, then it can switch to automatically to autonomous AP, right? And it will act like an autonomous AP because it lost connection to the controller, and it would still provide internet access to the devices in autonomous mode. And once the back end of the network, the controller and the switches and everything come back up, then it can go back into the standard local AP mode or the thin AP mode. Right? So that's what we refer to as a Flex Connect mode. And then there is a sniffer mode. It's quite interesting because most modern Wi-Fi networks are also enterprise networks are designed to do the troubleshooting and analysis themselves, which means that to actually do proper troubleshooting of what's happening on the network, you need to collect a lot of data. And one of the things you can do is you can deploy extra access points in a location and set some of the access points, or at least some of the radios of some of these access points, in pure sniffer mode, which means that here we are not actually advertising a Wi-Fi network on the access point. We are only sitting there and using the radios to sniff and collect packets and then send the data to the controller to do some analysis. And the controller can look at the data and maybe find out certain problems. So why a client not connect to an access point properly? Was there some form of a rogue device, some form of a problem on the network? We'll be able to find out. So the lightweight APs can also be programmed in monitoring mode, where they're not necessarily capturing packets, but they are monitoring the air interface and looking for certain anomalies and rogue devices. They're gathering some interesting analytics and stats of what is happening on the Wi-Fi network, how many devices are connected, what they're doing, and so on. And then providing that information to the controller so that the controller can do interesting things with that. Lightweight APs can also be configured in spectrum export mode, which is where, again, you're not offering a basic service set, you're not offering Wi-Fi network connectivity, but you're actually using the radios to do spectrum analysis. And it's almost like using Wi-Fi radio as a spectrum analyzer, and you're collecting various information about the signal to noise ratio, the power spectral density, the spectrum mass, the various RF related things of how much noise flow do you have in a location. All those RF characteristics and RF parameters are collected by the radios in spectrum export mode, and this data is again sent to the controller so that the controller can do interesting things with it. For example, if the spectrum export finds that channel 6 is a very busy channel, you're seeing a lot of interference, and maybe you're seeing non-Wi-Fi interference. Maybe there are some Bluetooth devices using the channel. That information can be sent to the controller and then controller can automatically change channels on the AP, for example. So then we also have the bridge mesh mode, in which lightweight APs can be configured to create Wi-Fi extenders and so on. So if you look at the wireless LAN controller deployment models, basically we talked about how the different modes in which lightweight APs behave can configure. So now let's look at the deployment models. So again, the most common model, at least it used to be the common model, it's changing a lot now, is what we call as a unified WLAN controller, where there is a physical controller on premise. So there's these controllers. So if you go to an enterprise and you go to their server room, or basically your wiring closet in the IT room, you will see a physical wireless LAN controller, and that is managing all the access points on campus. And that was predominantly the most common method in which wireless LAN controllers were deployed for many years. And the advantage with that is the controller is on premise, which means that the response times are very fast. And if there is a failover of the internet, if there is a failure on the internet, you're not suffering from that, because the controller is local in your local network. And in fact, you can almost create an entire local network and keep the network operational, even though there is failure on the upstream. The disadvantage, of course, is that controller is normally can be only managing one location, one physical location, and it doesn't really work very well when you have a distributed enterprise model. The another model is where you can have a cloud-based wireless LAN controller, and here it is not a cloud controller; it is only cloud-based, which means that or it could be a VM-based. So which means that rather than having a physical controller box for which you have to spend a lot of money, one thing you can do is you can take the software instance of that controller and run it on a virtual machine, either locally on campus or somewhere in the cloud, right? And mostly it's in a private cloud, it's not in the public cloud. So it is still like a normal wireless LAN controller. It is just that it is not being run on a physical controller box. Right? Again, in this model also you can manage thousands of APCs. And then we have another model in which a wireless LAN controller can be embedded into the switching fabric, or the switching network, right, in the local area. Now these are all local deployments. I'm not talking about cloud controller here. I'm talking on-premise controllers, right? So you can actually take the wireless LAN controller and put it inside the switch. Basically, you can do it embedded with WLC. And then even more advanced ones is where you take a piece of the wireless LAN controller functionality and run it on the AP, right? So now there is one AP in your network, and there are many companies that actually did this about 10-15 years ago, when they started creating these distributed controller architectures, where a certain functionality of the controller is run on each one of these access points. And there could be a master-slave model where one access point is the master, and it is running the controller functionality or certain parts of the controller functionality. And there could be another access point that is running a different a module of a wireless LAN controller. And the wireless LAN controller is now actually running in pieces on various access points in the network, right? So that is another interesting model for wireless LAN controllers. Okay, so that is basically like a physical controller and lightweight, using lightweight access points. So now let us come to the concept of a cloud controller. As I mentioned before, most enterprises started becoming more distributed, right? So the idea of having one large enterprise in one physical location is still there, but it's not as interesting as managing an entire distributed enterprise across many sites. So that's where cloud controllers came back. So now the interesting part with cloud controllers is all the advantages we had with lightweight access points, or many of the advantages, don't exist anymore. So what did we do? We took half of the AP's functionality, the upper MAC, and we pushed it to the controller before, right? And this only worked because the controller was in close proximity to the access point, and you have dedicated tunnels to the controller, high bandwidth tunnels. So you can actually send all the data from the access point to the controller, and it will still work. But with a cloud controller, you cannot do that, because the controller is sitting somewhere in the cloud, and it's really not practical for you to create all these tunnels from all these access points to the cloud controller. So what happens is the amount of information that can be sent from the AP to the controller has to decrease substantially because it's going over the entire internet cloud, which means that a lot of the functionality has to be pushed back now to the access point. So now a controller-based AP is somewhere between a fully autonomous AP and a lightweight AP. A fully autonomous AP does all the AP functions. A lightweight AP does very few AP functions, and a cloud AP, controller-based AP, somewhere in the middle, right? It basically pushes some of the functionality back into the access point, and all the management functions now are pushed to the controller. So a typical controller-based AP or a cloud-based access point talks to the cloud controller and exchanges very little information. Only basic configuration information, basic stats, and basic details are exchanged. And we cannot really have the very heavyweight CAPVAP protocols and all the encapsulation and all the additional overhead anymore with the cloud-based model. Right. So that's the kind of the plus and the minus of the cloud controller. So it's the plus is you can actually manage it from the cloud, and then the minus, of course, is you have to push some of the functionality back to the access point. So of course, cloud controllers can manage many things. So if you look at a simple example of a Marathi dashboard, so you can actually look at everything at an organization level. So this is an organization level of the dashboard of an example network. You can see all the sites, locations in one place, and then if you click on the organization overview, you can see all the networks that are across multiple sites, across various geographical locations. All the data can be seen. So you can see that this particular company has offices in San Francisco, London, Sydney. They have teleworkers in various locations. All of those locations and sites are all tracked from one centralized controller. And you can select any one of the campuses and then go into the details and see how many Wi-Fi networks are there, what type of devices are there. And this dashboard is not just managing the wireless network, but it's also managing all other elements of the network, like your switches, your firewalls, your cameras, your sensors, and many different other network elements are all managed. If you can go to any one of these access points and select that access point, and you can see all the devices that are connected to that particular access point. You can get a lot more details of where this access point is located, how many clients are connected to it, how many SSIDs it has, what traffic is being sent, what is the memory usage, bandwidth usage of this access point. And you can actually go and look at each and every device that is connected to the access point and get device level data. So this is what the beauty of a cloud controller. So from a single dashboard, you will be able to manage your entire network across many sites, and not just your Wi-Fi network, but your entire networks and systems can be managed from one location. You can select on cameras. You can actually look at each and every camera, watch the videos of live video from each of these cameras and so on. So it's a pretty extensive deployment when it comes to cloud controllers, right? And it makes the life of the IT person very simple. So that's about cloud controllers. And of course, after cloud controllers, we have even more advanced technology where we are trying to incorporate machine learning and artificial intelligence into the controller technology, essentially trying to take the IT person out of it, kind of not having to do a lot of work, right? Because again, the network is self-aware, the network is self-healing, and the way you do this is by collecting a lot of data. Or the only way artificial intelligence and machine learning works is by collecting a lot of data. You have to collect a lot of data, and from that data, you have to recognize patterns, and from that patterns, you need to identify behavior, and from that behavior, you need to basically learn things and change, right? That's really all what AI is about. So most of the advanced controllers that we have right now have all these gadgets where access points and extra radios that will get packet captures, that will sniff there, that will collect a lot of data, and then from that data run advanced machine learning algorithms to do various things like understanding the engagement of users, understand the behavior patterns of the users, understand how often networks are going down and coming up, understanding different kind of patterns, recognizing patterns, and applying corrective actions based on various patterns. right? This is all done by even more advanced wireless LAN controllers. I put the picture of Juniper Mist, but there are many companies that are doing this now. I mean, pretty much any wireless LAN company, enterprise company, they have advanced artificial intelligence features and several microservices that are running as well. So the idea is that the technology moved from providing really good Wi-Fi access, good range, good throughput, to providing ease of use, providing a number of services, and providing a lot of different features that will make the end user's life very simple, and the life of the IT person very simple. Now, of course, there is even more cool stuff that is coming out. We talked about cloud controllers and on-premise controllers and all that, but there is this again new, even more interesting things like technologies like Open Wi-Fi. Open Wi-Fi is trying to open source the controller technology. Most of the controllers, software, everything that we showed so far is pretty closed. If you have Cisco, they have their own controller, they have their own protocol between the access points and controllers. Whatever they're deploying in the cloud, it's all closed, and it's Cisco's technology, it's Aruba's technology, it's Juniper's technology, and so on. But for the first time, the Open Wi-Fi is really trying to open up the Wi-Fi technology and open source cloud controller SDK and so on. So this will allow us to create disaggregated networks. So what that means is you can have the controller in the cloud, and you can have an access point from one vendor, part of the cloud. You can access point from second vendor, and access point from third vendor. Many different access point vendors who are part of the Open Wi-Fi basically group can deploy access points that will all talk to the same controller. They're all provisioned by the same controller and then managed by the same controller. So this will allow for disaggregated networks where many different vendors can be part of the same Wi-Fi network, and hence it opens up the doors for more business cases and more competition, and it reduces the cost of network. Right. Open Wi-Fi also has a lot of really cool features. If some of you are interested in looking at Open Wi-Fi, it is super awesome. So and it's in par with many of the closed technologies. They have so many features for various enterprise use cases, and I just listed some of these features from their website. You can see, if you look at an Open Wi-Fi access point, it pretty much supports all the features that you would see in a typical enterprise class access point. If you look at the Cloud SDK also supports lots of features, and it provides a lot of interesting, really good APIs, northbound APIs. So if you want to add your own functionality and your own special things on top of the controller SDK, you can do that and create your own applications, right? So it's very, very flexible and has lots of really good features. You can certainly check that out. The last kind of use case I want to talk about is where this concept of PM Vani, which you are starting to see in India, which is the idea here is that how about you make the entire country a distributed enterprise? So we talked about like an organization being a distributed enterprise, like say a company like a Microsoft or Apple or some other large Walmart or Starbucks. They could all be distributed enterprises, right? But what if you can make the entire country a distributed enterprise, where you can actually have what we call as a government-operated wireless access network, where you have these public data offices or PDOs, which are essentially small Wi-Fi networks that are installed in various public places, like in municipalities or in village offices and small convenience stores and so on. And they're all aggregated using a PDO aggregator, and then you have a central registry that is maintained by an organization like CDOT. And now you basically have a large enterprise network, a distributed enterprise network that spans the entire country, and that is managed by a central location. And that is a very interesting idea. I mean, PM1 started deploying access points, and there are organizations like CDOT and others who are basically part of this program. But it's a very ambitious project, and it probably takes several years to implement. The idea really here is, can we provide affordable Wi-Fi access to all corners of the country? And the more we connect the country, the more we actually grow the country, and the more we have better business operations, and that helps in the economy, right? That was the idea. So So that's one of these interesting projects that, again, you can go and check it out if you're interested. So that's it for this. So to summarize, we actually went through all the residential use cases, ways in which residential Wi-Fi routers work, manage unmanaged networks. Then we talked about enterprise. We talked about autonomous APs, lightweight APs, having split MAC architecture. We talked about cloud controllers and controllers that are doing self-aware networks, artificial intelligence, machine learning, things like that. We talked about disaggregated controller networks, architectures like Open Wi-Fi, and we also talked about the entire countries and enterprise using areas like PM1. So hope you found this session useful.